So I'm going to start with the question, why study satisfiability? Okay, so of course we talked about why study logic and so on and so forth, but why study this problem of satisfiability? This problem of satisfiability is important because it's a canonical NP complete problem. Right? We all know it's an NP, and we all know that any NP problem can be converted into a SAT problem. So if you have a traveling salesman or graph coloring or subset selection or whatever, I mean various problems, you can convert this problem into a SAT problem. That is the first problem. So by just studying SAT and by creating solutions to SAT, we have implicitly solved so many problems. Solved or have an ability to solve. That's a ton of the applications part. But as I was saying, the current solvers today are super fast. They are incredibly fast. Of course, it's an NPL problem, so you shouldn't expect magic, but they are very fast. So this is where all the situations where logic has been applied, SAT formulas have been applied. So car repair diagnosis, mission control, chess playing, military logistics, hardware software verifications. Here we are talking 500,000 variables and 1 million constraints. If you think about the size of the state space, if you have n variables, you have 2 to the power n possible assignments. So we are talking about search in 2 to the power n space. So right here is number of atoms on Earth, 10 to the power 47. So maybe if we used all the atoms in the world, we could have done car repair diagnosis by brute force, but definitely not mission control. And these are all the problems in which satisfiability reasoning has been applied successfully. Here's a simple scenario, and we are going to go through a couple of examples because last time when I gave this project or this assignment to my students, they had a difficult time. Really, this assignment was the hardest for them in the 4 assignments. So I am assuming that the same is going to happen to you. So these couple of next weeks are going to be critical for you. And I'm giving you some support on starting to think about modeling problems as SAT. Okay, so this is the next 15 minutes. So here's a problem that I have, and unfortunately I did not revise it, so we'll solve it together. So we have to diagnose a malfunctioning device like a car. We know the design of the device, so we know how the device works, but we can observe only a certain part of the device. A lot of it is hidden. And so the idea of model-based diagnosis is that we should first create a logical formula that describes how the device should work. This is like my knowledge base. This is the knowledge base of what I know my world to work with, right? So an example would be to say, okay, I will say a component C is okay as my variables. Now if I want to do diagnosis, then what I will have is some observation that I have seen that, say for example, car is not working or something is not happening right. And I have to find a set of assumptions that are consistent with what is observed. That is my diagnosis task, right? So if I know that car is not starting, then my diagnosis task is to figure out what could be the reason. Okay? I have to come up with a set of answers, hopefully a small set of answers, that is consistent with the way the knowledge base works, consistent with the way the car works, and gives the observations that I want to have. So let's take an example. Okay, so this is going to be the algorithm. You have some observations O. You initialize the assumption set A to assert that all the components are working properly. If all the components are working properly, then your knowledge base, your assumption set and observation set together are inconsistent, right? Because something went wrong. So if everything is working properly and something went wrong, you should be able to deduce false as a first principle. Then what you do, you remove some assumption from the assumption set. And then you should not be able to deduce false, in which case the deleted proposition is a possible diagnosis. And there can be many possible diagnoses. So here's the example. I can observe that engine runs, there is tank in the gas, and clock runs. These are the things that I can observe. What I cannot observe is whether fuel line is okay, the battery is okay, cables is okay, and clock is okay. Hidden non-assumable propositions. These are not possible flaws. These are not possible diagnoses, but these are important in order to make the whole knowledge base work. So, for example, whether there is gas in the engine or whether there is power to the plugs. Okay. Now, my device works the following. If there is gas in the tank and fuel line is okay, then there will be gas in the engine. If there is gas in the engine and there is power in plugs, then engine will run. If battery is okay and cable is okay, then there will be power to the plugs. And if battery is okay and clock is okay, then the clock will be running. Now I observe that engine is not running, there is gas in the tank and clock runs. Engine is not running, there is gas in the tank and clock runs. Stare at it and think about what could have gone wrong. Sorry, if battery is not okay, this won't work. Battery could be the problem.
Battery with cables.
Cables could be a problem.
Cables is a fuel line.
Fuel line could be a problem.
Yeah, what he said. Cables are fuel line. One or the other.
Right. So how would you diagnose? We will say, let us assume that there is only one fault in the system. So first thing that we know is that if all of these things are running all right, then we can deduce false. Right? Because the fuel line is okay and then there's gas in engine. If battery is okay and cable is okay, then there's power to the plugs. If both of these are true, then engine is running, but engine is not running. So there's an observation that engine is not running, so something is wrong, so we can deduce false. Now, let us remove 1. So let us remove fuel line not okay. Now can I deduce false? If fuel line not okay is removed, a fuel line okay is removed, can I deduce false? So that is where SAT formula will come in. So you will give it a formula which says engine is not running, gas in tank, clock runs, these are the clauses. This is a clause, this is a clause, this is a clause, this is a clause. Battery is okay, cable is okay, clock is okay. Give me a satisfying assignment. And if I can get a satisfying assignment, then we will be able to prove that fuel line okay is a diagnosis. Similarly, you will be able to prove that. So similarly, we can try with battery not okay, and just battery not okay will not give us a diagnosis. Why? Because clock is running. Because clock is running, battery has to be okay. That's it. So this is one example of using satisfiability for diagnosis. And let's skip. Now, Deep Space One, which was a NASA space engine, space machine,
Space program.
space. Sorry. it had a diagnosis and repair system which was completely logic based. So it had essentially all the systems were compiled into 7,000 variables. It's not too much now by today's standards, but this is 1996 SAT problem. Now they ran this AI agent in this real experiment in space, and this AI agent was able to automatically diagnose the faults and repair them, suggest actions that will repair these faults. Now what really happened in reality is nothing went wrong. Because nothing went wrong, we could not test the logical system which was running the spacecraft. So because they really wanted to test us, they said, okay, let us simulate faults. Simulate as in tell the system that this is going wrong and see if it can predict the right things. So for example, it failed in electronic unit and remote agent fixed it by reactivating the unit. A sensor was giving wrong information, false information. Remote agent recognized it as unreliable and therefore correctly ignored it. And then finally, an altitude control thruster was stuck in the off position. Remote agent detected it and switched to a different mode that did not result in that thruster. So from an AI perspective, again now this looks quite trivial and not that exciting, but from an AI perspective, this was actually a huge deal. Because up until then, the only success that we had seen that is significant and worth huge was Deep Blue. And Deep Blue was awesome, but it is playing chess. So chess playing is great, but it's not a real application. As in, it's not an application that really is useful for us. Now you can argue whether a spacecraft is really as useful or not, but it was a real system, a real functioning system where this AI agent was controlling it, and that was considered super awesome at that time.
Something went wrong, that would have been more awesome.
If something really went wrong, that would have been even better. Testing circuit equivalence is again done by SAT formula. So you create a SAT formula for one circuit, you create the SAT formula for another circuit, and you ask, is there an input for which the two circuits compute different values? And if they compute different values, then your SAT formula will be satisfiable, but these circuits will not be equivalent. Let's do translation from n-queens. We have been studying n-queens for some time, so we should be able to do this. And this is what I'm going to ask you. So think about it. I want to create a problem, which is a SAT problem. The solution of whose problem is a solution to n-queens. So the first question, and the reason I'm going slow is because this will be very useful for your assignment too. So you have the first problem you have to figure out is what will be the variables. So what might you think could be the variables if I want to solve n-queens problem using SAT?
Squares of the board?
Squares of the board is a variable. And what will be the value?
Has or doesn't have.
A queen. Perfect. So the squares of the board will be the variables xi comma j, and we want to say that its value is true if there's a queen sitting there, and its value is false if the queen is not sitting there. Okay, it's a great start. Now we want to add clauses which are true. Let's intuitively add a clause and then we'll later convert it to CNF. So what is the first clause we need to add? Awesome. Give me a clause that I need to add. Yes?
One queen in a column.
Only one queen in a column. How can I add that clause? What will it look like?
So we'll have 8 clauses.
Wait.
Yeah, it looks like you can't, only one of them allowed to be true. So
yes.
Given any pair, only one, you can't, given any pair of, in the column, you can't have both of them be true.
Given any pair, you cannot have both of them to be true. How will you translate it into Give me one example of a clause.
Oh, easily it's. Not
Suppose I want to
two.
say that x11 and x12 are in the same column.
Right.
So they.
Say not x11 and x12, which is the wrong form, but let's start there.
Here is an easy version. What does x11 imply? Easy to think in implications. X11 implies not x12. Now let's convert it into a clause. It is
Not x11.
X11 implies not x12 and not x13, a bunch of not.
yeah. I agree with you. But let's do one pair first. So x11 implies not x12. We can all see that. Converted into a CNF formula or a clause, it becomes not x11 or not x12. We have to do
the
it.
other way and apply to Morgan's law and you end up with exactly.
No, this is a clause.
Yep.
Right, this is already a clause. So now we will have how many clauses in a column? 8C2.
And choose two.
8 choose 2, right? For all the columns, and for all the rows, and for all the diagonals. Fine, it's alright. That is the conversion process. It feels like an inflation. Yes, it becomes like a large formula, but we'll talk about the fact that we can solve them. So we will create lots of these clauses. Anything else that has to be true? Now, this is a tricky one.
Yes.
Mike,
And at least one in each column.
good point. Can I set everything to false for if I only had these clauses?
Yes.
And this is the thing that we miss when we are converting to SAT, because this is not intuitive, right? So far we have only said that there cannot be a queen at x11 and also at x12. But we have never said that there has to be any queen at all. So there has to be one queen in, what was your suggestion?
In any of the columns.
In any column. So how would we say that there has to be a queen in a column?
X11 or x12 or x13.
Exactly. That's it. The only difference I have in the slides is that I am using Q1 now. So this is the clause which says at least one queen in each column, and this is the clause that says no attacks. So it's not very hard, but it is not intuitive if this is the first time you are seeing this. Alright, here is another example just to drive home the point. Give me any CSP and I can convert it into a SAT formula. We have a Punjabi sheet.
So we don't need the constraint that there should be one queen in every row.
Because as soon as in this particular case, because if there is one in every column, then we will have to have one in every row, but you may
Like throwing them in here will
not hurt you.
not hurt me.
So here's an example which shows that you can convert any CSP to a SAT problem. So CSP, so the variables will be X variable value. So Western Australia red, Western Australia green, Western Australia blue, Northern Territory red, and so on and so forth. Each variable should have at least one value. That means either Western Australia is red or green or blue. No variable has two values. So either Western Australia red is false or Western Australia green is false. Constraints. So Western Australia red, that means Northern Territory cannot be red. So both of them cannot be red together. So that is encoding the constraints. That's it. So CSP and SAT are interchangeable formats. And there are many other examples in the literature on converting things to SAT. So here is an example of a formula that we are able to solve. Okay. So here this is the syntax. Not x1 or x7. Not x1 or x6. Not x17 or x22. Not x177 or x169 or x161, and so on up to or not x185. This is 10 pages later. This is about 4,000 pages later. One of the clauses is a 59 CNF clause. And finally the formula ends 15,000 pages later. There are 50,000 variables. The total space is 2 to the 50,000, which is 10 to the power 15051. And in 2002, we could solve this in less than 1 minute. There is a reason why I want you all to learn SAT and force you through this process, because if you ever get a deterministic NP complete type problem, this should be your first solution. Don't think about the problem too much. Convert the thing into SAT and run a SAT solver on top of it. See if it works. If it doesn't work, sure, you have lots of time to think about it. But this is the first thing that I would like you to try. And then think a little bit about creative translations into SAT, because a better translation into SAT will take you much further than you thinking too much about the problem. Sorry.
So it can take you years to come up with 15,000 pages of.
Somebody automatically, clearly, you will have a problem description and you will write a code to translate into SAT.
What problem is this?
This is some bounded model checking problem. So this is the point that I want to make. In the last 20 years, we have a huge amount of progress, where we have gone from 100 variables to 1,000,000 variables, and to be honest, you can encode a lot in 1,000,000 variables. It's not Moore's law, because Moore's law is only making your speed go double, and if you are doing brute force search, that means one extra variable. So it is not Moore's law. It is much more than that. In fact, we have developed some very beautiful theory which I wanted to get into, probably will not to that extent, about SAT solvers. But here's the way it has happened. Every year there is a SAT competition, or every other year at least, where the benchmarks are industrial benchmarks. They are real benchmarks. The people in industry want these problems to be solved. And lots of competitions, lots of solvers from all universities and elsewhere compete. And that is how progress is happening. So this is your problem. And it is a beautiful scenario about it, but about intelligence and terrorism and whatnot. But let me get to the core of it in the class. You have two directed graphs, G and G prime. You want to figure out whether G is a subset of G prime. And where a subset is defined as follows. You have to figure out a mapping from all nodes of G to some node of G prime. One-to-one mapping. Such that if there is an edge from N1 to N2 in G, then there should be an edge from the equivalent mapped versions in G prime. And if there is no edge from N1 to N2 in G, then there should not be any edge in G prime. Simple problem. Is there a mapping from G to G prime? Is there a mapping from G to G prime?
Yes.
If there is an edge not in G, then that edge should not be in G prime. Is there a mapping from G to G prime?
No.
Because the edge from A to C is not there, therefore the edge from P to R should not be there. Is there a mapping from G to G prime?
Yes.
What's the mapping?
SQR.
And, sorry?
SQR.
SQR. Correct. So your goal is, given two graphs like this, spit out a mapping like this, if it exists. And your method is, you have to convert this problem into a SAT formula, run an existing SAT solver, not the state of the art, but a very simple to understand SAT solver. If you are interested, you can actually go inside the code and understand the DPLL that is happening there. So it's a decent SAT solver, not just DPLL, more than that, but simple algorithm, still not the state of the art. And it will run, and if it spits out a solution, then you will have to take the solution from the SAT formula and convert it into a mapping. So you have to write a translation process and a assignment interpreter. And here is my recommendation. If you are really learning logic for the first time, I would encourage you to make a team of 2. Ideally with a person who has learned logic before. Because I do not want you to go through the same experience which your predecessors went when they did this problem. But it is important to do this problem because you're learning something important that I believe is important. If you have learned logic before, then it's fine. And I think the examples that we went through in N-coins and so on will guide you. And again, we are there. If you have any questions, DJ or me, you can send us email. We will be happy to. Any questions before I move on to the advanced stuff? Yes.
Do we do this one in Java as well?
You can use any programming environment as long as DJ can run it on his machine. Because at the end of the day, we will create a benchmark problems for you, and you will have to show that your algorithm can scale to larger benchmark problems. So there's always there will always be a little bit of incentive for you to do a good job. And good job is in the sense of think carefully about what would it mean to make it a good running system. That doesn't mean write the engineering sort of write comments in your code, but that would mean that it should scale well. It should not be a very brute force input. Yeah.
So there are 3 possibilities here. The mini-SAT can spit out a solution, which is the actual solution. It can return false, empty, which means there is no solution or it may not terminate or something like that.
Yeah, so if you have a good encoding, if you have a bad encoding, there will be problems where it doesn't terminate in a cutoff limit. If you have a better encoding, then you might be able to scale better. But the way we will do it is that we will have some cutoffs. But those cutoffs will be problem dependent. It doesn't make sense for you to worry about it.
I think the assignment says the problems will be randomly generated, so it's not guaranteed if you totally generate randomly that within that cutoff you will always satisfy.
But you will all be tested on the same problem. So if mini-SAT doesn't spit, it doesn't spit.
So can you use a logic programming language like Prolog?
No. So yeah, use it. Yes.
In the sample data that you're going to give us, are you going to give us a correct answer so we can know that we're doing?
There's no sample data. You're given a problem generator. So you can generate your own problems. And there is a checking function which shows whether your mapping is accurate or not. And the problem generator can be given a flag which says, give me 2 graphs which there is a mapping. So you can play with your sizes of the graphs yourself at your end. Yes?
A correction in the problem description. Maybe it doesn't matter, but it says, like you are saying in the problem, if there is an edge here, then there is edge there. But if there is not an edge here, there should not be edge there. That is not in the description. So like it would mean if a person...
Yeah, use this graph, use these examples as your guide. I'll correct the description, send me email. I think Nat already sent me that email. Any other questions? Okay, in the remaining time, we will cover some material about how these SAT solvers have become so interesting. So before that, the one algorithm that we haven't covered so far, which is the greedy hill climbing version. So we have covered the backtracking search version of it, but there's an equivalent greedy hill climbing version. So the greedy hill climbing version goes by the following: pick an unsatisfied clause, and with a high probability, flip a variable that minimizes the number of unsatisfied clauses. So that's the greedy step. Okay, so now we are doing local search. Local search means we'll start with a complete assignment, not very complete assignment. So it's not a partial one variable assignment at a time. In all local search, we typically start with an assignment that is a solution or a potential solution because we don't have any history. So we have a full solution at hand. It satisfies some clauses, which is great. It doesn't satisfy some clauses, right? So we go over the list of variables, and if define our neighborhood function as flip one variable. You've done local search assignment, this should make sense to you. We flip one variable, that will be our neighborhood function. So all the other variables assignments remain the same, we flip one variable. Which variable? Now let's do the greedy step. So the greedy step says flip that variable which minimizes the number of unsatisfied clauses. That's the greedy hill climbing step. So far so good? Then with some probability do a random walk. And if you remember our whole conversation on local search, just greedy hill climbing doesn't always work. We have to add some intuition. So here we are adding the intuition that you will do a little bit of random walk. So with small probability, flip any one variable, any one random variable in any one unsatisfied clause. So pick a clause at random and pick a variable at random and flip it so that it becomes satisfied. This is called GSAT. This already was beating the heck out of DPLL some time back. So the best algorithm for random KSAT, DPLL was able to solve 700 variables in the late 90s. WalkSat was able to solve 100,000 variables. And this we have also discussed in the past. For n queens, WalkSat was able to, local search is able to solve up to 25 million queens and things like that. Right? So it scales much better. Of course, if a formula is unsatisfiable, this won't tell you. It will just keep searching. So that's the problem. And then it may not always find the solution. Now this gets refined into something called WalkSat, which is the most competitive version of this. This was actually around early 2000, if I am not mistaken. Now the reason we are doing the random walk is because we want to get away from the local optimum. So when the problem becomes, most of the variables are assigned and there are just a few handful of variables, clauses, that we are not able to satisfy, what happens is that pretty much each flip is only going to make one clause true. Might make lots of other clauses false, but it's most likely going to make just one clause true. So for each variable, we assign this number, makes a clause, the number of clauses that it makes true, and breaks, number of clauses that it makes false. So of course, if it breaks nothing, we should assign it. But near the solution, it's mostly the break count that matters because the make count is usually 1. So what WalkSat does is that it does something slightly cleverer. It picks a clause that is false. Sorry. No. So for each variable, it computes the number of clauses it's going to break. If there exists a flip whose break x is 0, then it deterministically chooses that. However, otherwise, it with probability p picks a random member in a randomly chosen clause, which is the exact random walk step that we had in GSAT. And otherwise, with 1 minus p probability, it minimizes the number of clauses it's going to break. So it's just a small modification. Basically, this is the main modification, and this is the slight variation on flip the best one. But bottom line is that it's doing pretty much very similar to greedy hill climbing. So now, this was extremely competitive. Moreover, what happened was it was solving everything. So these guys said, we are solving everything, so we should push ourselves. We should construct problems where we are having a problem. We will be able to solve with a lot of difficulty. Then we will beat everybody else much better. Okay, so this was the game they were trying to play. They said, we are going to create problems which are extremely hard for us. But if they are so hard for us, they will be extremely hard for everybody else. So in that space of problems, we will do much better than every other algorithm in the world. Because at that time, the most real problems, everybody was able to solve. So they wanted to say that we are much better. In the process of trying to, So they said, how can we construct hard problems? Right? This is the question that we should think about. If I have 1,000 variables and say 10 clauses, will this be an easy problem or hard problem?
Ooh, wait a minute, you got lots and lots and lots of variables and very few clauses.
It's going to be, well, you just have to set something true and the whole clause disappears.
So
that should be very easy to solve.
because there are so few constraints, we can basically satisfy each constraint somehow or the other, and most likely, more or less, we will be able to solve it. It's an extremely easy problem. If I have 10 variables and 2,000 constraints,
There's exhaustive search in blink of an eye anyway.
right. No, you're right. But is this an easy problem or a hard problem?
Easy because variables are less.
Very few variables.
Yeah.
So is it most likely going to be satisfied?
No.
You will not be able to satisfy it. So there is a procedure called unit resolution, which I didn't get into, but that can, in polynomial time, often prove that something is unsatisfiable. So usually with greedy hill climbing approaches, they add unit resolution. So the idea being, around here, the problem is going to be mostly satisfied. You even give it a random assignment and you would be able to satisfy it when your number of clauses are very few. On the other hand, if the number of clauses are extremely large, then the problem is most likely going to be unsatisfiable, and so come what may, you will not be able to satisfy it. Moreover, with some polynomial algorithm like unit resolution, you will be able to easily figure out that it is unsatisfiable. So these are the points that we are sort of aware about. You can guess. It's like this. Suppose you have this SAT problem as your assignment, and you have a year to do it. You will be able to do it. Suppose I give you 100 such SAT problems and say you have to solve all of these 100 problems in this weekend, and you get credit only if you solve all 100 problems. What will you guys do? Watch a movie. Because you know that in the rational mind, nobody will be able to solve all these complicated 100 encodings, write code for it, and submit it in 2 days. So who cares? Let's just have fun. So this is clear, easy, solved. Clear, easy, difficult. So you expect that the harder problems will be somewhere here, where you might just satisfy it. It's like on the knife edge. So one would hope that the satisfiability count will go something like this, and one hopes that somewhere here the hardness will happen. So easy, hard, easy. Okay. Now, as these guys are doing these experiments, they actually found that this is obviously intuitively true, but not quite. What happens in reality is this and this. That there is a sudden transition from being almost easily satisfiable to almost satisfiable with a lot of difficulty and not satisfiable. A sudden transition.
These are from random SAT problems?
Random SAT problems. And moreover, it happens when this ratio is 4.3.
That's random.
For 4.3 for 3 SAT formulas, sorry, just to be clear. This is the real data. And this complexity peak of where the problem is hard happens to be invariant of the algorithm. So you do DPLL, you do WalkSat, you do whatever. This is where it is going to happen.
What is 3SAT?
3SAT is a SAT formula where all the clauses are length 3. And it's the first NP hard problem, because 2SAT is a polynomial problem. It's in P. 3SAT is the NP hard problem. And as your number of variables increase, this peak becomes, this suddenness becomes even more dominant. So this is the space where things are problematic, because they are on the knife edge between SAT and unsat. this is called phase transitions in SAT. And moreover, this is similar to, your boiling water. At 100, before 100 degrees Celsius, it's liquid. And then as soon as it goes past 100, all water wants to have fun and evaporate, go away, change the phase. So the same kind of phase transition happens in SAT.
You're a PhD in the answer to that question.
People have not been able to prove it, that it will happen exactly at 4.3. People have been able to empirically observe that it will happen about at 4.3. The other thing people have been able to do is to prove where it will happen, what interval it will happen in. I actually had a proof, but never mind. So, as different algorithms are maintained, so if you are just doing random walk, then you are only able to solve up to this point. But as this is DPLL, this is better DPLL, this is GSAT that we just did, this is WalkSat, this is the recent most algorithm, survey propagation. So you are getting closer and closer to the problems that you are able to solve. This is the region where the problems are solvable. So as newer algorithms developed, they were able to push the limits of this region of where they were able to solve the problems. Okay? But this has been lower than 4.3. On the other hand, you can prove by combinatorial arguments as to what will be the tipping point where on average all problems will become unsatisfiable. Okay, and combinatorial arguments, at least the first one which says that it will happen after 5.19 is actually trivial. We will spend 10 minutes or 7 minutes and you will be able to prove that after ratio of clauses to variables greater than 5.19, on average a random problem will have 0 solutions. Random problem. But then you can do better and better bounds by better and better combinatorial arguments. And this was the state circa 2004. Maybe these bounds have gotten closer. So here we knew that the right answer is between something around 4.2 and 4.5. Empirically, we have observed it to be 4.3. This is as much as I'm going to say, given the time. But if you have any questions, you should ask now about this particular phenomenon. Yes. For SAT, I think it's around 7 or 8 or 10 or something. I don't know the exact numbers, unfortunately. But yes. And by the way, this is not just for SAT. CSPs also have this phenomenon. So pretty much there is this satisfiability to unsatisfiability phenomenon that is observed over and over.
And CSP is convertible, so if this has a phenomenon, that will...
Exactly. Anything else? No. All of this we studied for random SAT problems. As AI researchers, do we care for random SAT problems? Actually, we do not care for random SAT problems that much. I mean, it's good to understand. This is a beautiful phenomenon, so it's great to understand it. But really, in reality, we care for real problems. And real graphs are different from random graphs in some very interesting ways. So first of all, real graphs have short path lengths, but that is also true for random graphs, typically. However, there are parts of real graphs which are highly constrained, very clustered, very dense, subsets. That doesn't happen in random graphs at all. So, here's an example. First of all, the fact that we have short path lengths. We all know about 6 degrees of separation, right? So we know that even on Facebook, I can go from any person to any person in pretty much 6 hops or 5 hops or so on and so forth. That's not just Facebook. This applies to US electricity grid. This applies to the neural network of a worm. It's actually a general phenomenon that if you have a large network, real network, modeling real phenomenon, quite likely the diameter is going to be really small. Or yes, or the average path length will be extremely small. Secondly, at the same time, on Facebook you find this cluster of 50 friends who are all connected to each other. or 100 friends or 200 friends who are all connected to each other, and many clusters like this. If you try to regenerate a random Facebook graph with same number of edges and same number of nodes, you will not see this phenomenon. This is because a random graph is generating an edge randomly. The real world has more structure to it. So here's an example. This is an exam timetable scheduling problem in Edinburgh University. 59 nodes, 594 edges. Relatively sparse. But it had a 10 clique. A subset of 10 nodes which were all connected to each other. There is a less than 10 to the power minus 10 chance in the random graph to observe this, assuming the same size and density. And moreover, the time taken to solve the problem was totally dominated by this clique. Right? So studying random graphs is fine for understanding, but real graphs and random graphs are different, and we have to study real graphs for real graphs, because and if we can identify those structures, then we can solve the problems even better. It's the goal. That's some of what has happened in the recent times. So here's an observation that I'm going to give you. DPLL. Suppose I did DPLL and somehow randomize the variable selection. Okay. Then you will find that some runs will take forever, never finish. And some runs will be solved like this. Or similarly, if I take similar problems, no randomization, but same size problems, say took 1,000 of those problems, and ran DPLL, you may find that 50% of those problems got solved like this. And then some problems never finished, kept on going, kept on going, kept on going. Here's an example. Here's a set of critically constrained problems, medium constrained problems, and under constrained problems. And you hope that as you increase the number of backtracks, you will be able to solve more and more problems. So this is the unsolved fraction. So all the curves should go down. If it is under constraint, it will go down fast. If it is critically constrained, it will go down slowly. Fine, we can all expect this. But notice, this is a log scale, this is a log scale. So, what does it tell me? 50% of the runs, one backtrack is enough. And for this critically constrained, or even for medium constraint, 10% of the runs we could never solve in even 100,000 backtracks. There's something happening here which we are not able to understand and pinpoint, but there's something clearly happening here. There's a big heavy tail distribution. So the first solution that people thought is that let me randomize the restarts. So let me pick a random variable order and just do a small number of backtracks and then just restart. This is very similar to our random restart in local search, but it's very different. Because in random local search restart, we're starting from a full assignment and going up to the top. Here we are saying that we will do very few backtracks. This is partial assignment. And if by unit propagation in pure literal business, by polynomial inference, I am not able to solve the problem in a small number of backtracks, then I just restart with a random variable order. So it's a very different strategy. So now let us see the phenomenon. No restarts for the critically constrained. We're just solving, not getting anywhere. Restart after 4 backtracks. This is ridiculous, Just 4 backtracks. Oh, I'm just gonna restart. So this is pretty cool. The observations, I'm not giving you the answer yet, but I hope to give you the answer also as to why this is happening.
So what do you do when you restart?
You just start with a different variable order.
You shrink that, you throw it.
You throw the search tree, you restart the search tree with a different variable order. And keep doing the polynomial inference, which is unit propagation and stuff.
Rather than 5 or 3 backtracks.
Yeah, I'm sure similar. In fact, so notice with 4 restarts, in about 250 backtracks, which means 62 reruns, we are able to solve 99.9% of the problems. Or 99.999, yeah, 99.9%. Now, if you plotted the total number of backtracks with the cutoff, which is the restart cutoff, then you realize that if you did not do any cutoff, then your total number of backtracks is huge. If you cut off after if you cut off too soon, then your total number of restarts is huge, and therefore total number of backtracks is huge. If you cut off really late, then your total number of restarts is very less, and the total number of backtracks is huge. What happens is there's some sweet spot often. So this is an example of 100,000 backtracks if your cutoff is 10,000, which means that I got to do 10 restarts. Here's an example, if my cutoff is about 20, then most of the problems got solved in 2,000 backtracks, that means about 100 restarts. So there's a sweet spot with a small number of cutoff. Cutoff is the number of backtracks I allow before which I throw and restart. Okay, so these are the observations. There are several ways to randomize the variable order, but we'll skip that. I get straight to the meat, straight to the point. Why is this happening? First of all, you must realize that as soon as I make some commitments, I say x1 is true, x2 is false, x3 is true, I have gotten down the path. If these commitments are wrong, that means there is no solution in the subtree. How much time am I going to take before I come back? I have to search this whole subtree. So many backtracks before I can come back and remove my first commitments. So early commitments have a huge risk, right? Do you agree with that? That my top choices is the bad direction. It's like I started doing major in some field that I started hating later. Very costly. Yeah, exactly. Now, so we can explain why some problems may take forever, right? The intuition is because they are doing this exponential subtree before coming back and making those changes. But it still doesn't explain why am I able to solve problems after randomization so quickly. Are you with me in this notion? At least some of you, yes. I mean,
so that means why are some initial choices
so good?
Yes, that's your question.
That is my question. We know why are some initial choices so bad, but we still don't know why are some initial choices so good. The formalization of this is called backdoors. The idea is that real problems, not random, real problems have hidden, tractable substructure. And that is why we as people are able to solve those, because there is some structure that we are able to recognize. Of course, we recognize it. We go one step further, we see some abstraction, we see that if I make this variable this, that variable that, then suddenly everything fits. The computer may not be able to recognize this explicitly, but there is some structure in reality. And we will formalize it by calling backdoors. So what is a backdoor? Informally, a backdoor to a problem is a subset of variables, usually very small subset. Once they are assigned that values, those specific values that they need to be assigned, then the remaining formula becomes extremely simple. In fact, the polynomial propagation is going to be able to solve it. The intuition is there are some variables. As soon as I assign them, everything else becomes simple. That is the backdoor. That's the back channel to solving this problem. This is the formal definition. It says, a backdoor with respect to an algorithm A is a non-empty subset of variables such that as soon as I assign those variables to the specific assignment, A, the algorithm, will quickly or will return a satisfying assignment. And A is typically the polynomial propagation. And a strong backdoor is when the A will also tell me that the formula is unsatisfiable. But let's not worry about strong backdoors. There are beautiful connections with cycle cut set that I'm going to skip. And I'm going to get to the point. The point is, there are 2 points. Point number 1, most real problems have really small backdoors. There is some structure, some variables, very critical variables. As soon as you set them, you're done. Of course, what's the challenge? We don't know those variables. Let me finish this discussion. We don't know these variables. Because we don't know these variables, and I'm sure finding these variables is NP hard. Because the problem is in NP, obviously. What could we do? Now, does this make sense? Do you think random restart will help here? I randomly picked the first few variables, made these commitments. If it did not work out, I still made some more commitments and restarted and made more commitments. And if by chance I picked the backdoor variables and set them to the right values, then running will already becomes trivial. So by doing this over and over and over, my probability of picking the backdoor variables and setting them right becomes very high, because these backdoors are typically small. So here are some examples. Logistics domain, 12 backdoor variables, some bit adder 53. I don't know where these problems are coming from. But the point is that these numbers are usually small, even though the number of variables may be large. Now, seeing is believing. So this is the constraint graph of a 843 variable problem. The backdoor set is 16. As soon as I set 5 variables, this is what the constraint graph looks like. And if I set 12 variables, this is what the constraint graph looks like. Pretty much solved. The problem is almost solved at this point, by setting these 12 variables and just propagating information. Here's another example. Backdoor of size 3. As soon as I set those 3 variables, this is the problem. Actually set 2 variables, this is the problem that remains. Last example. Inference problem, 1650 variables, backdoor of size 40. Set 6, set 38. So real world structure is hidden in the network, and the automated reasoning engine, by using sampling, by using random restarting, is able to exploit that. And so therefore, and this just shows what happens for current solvers. If you heuristically pick the variables to assign, and your backdoor is size constant, solved in polynomial time by random restarts. If backdoor size order log n, usually solved in polynomial time on average. Even if it is linear or a fraction of a linear, a tiny exponent. So that is why some of the successes of SAT solving has happened, especially in the systematic search playground. The greedy local search we can understand somewhat, but in the systematic side, by using random restarts intelligently, we have had immense success, and then later people thought and tried to study why, and they came up with this beautiful theory of backdoors. There are some other techniques that I did not get a chance to get into. Some of them are very useful also for CSPs. For example, no good learning. It says that if you come to a point and you fail, you take some learning from it. So you figure out what subset of variables caused this assignment to fail, and then later never get the same subset of variables to reappear in any other part of the search space. That is called no good learning, extremely powerful in practice. where the current research is headed, people are doing machine learning. So they are saying, given the problem, can I automatically figure out which algorithm will be the best algorithm for it and allocate time, small amounts of time to different algorithms in an automated way. That's the other set of techniques that people have worked on, and there is some interesting research that people are working on right now, which we need not get into. So you had some questions. We should just take them in the last 2 minutes.
For something to be considered a backdoor, does it have to eliminate backtracking entirely, or just minimize it to very?
For something to be considered a backdoor, notice that backdoor is with respect to a subsolver. So if your subsolver is just a polynomial propagation algorithm, then for something to be considered a complete backdoor, it needs to completely get rid of the backtracking, and it should just propagate everything. Because in practice, we allow some number of backtracks just to balance this out. You had another question. Yes.
So in the CSP thing, we had a way of choosing which variable to start with and which one to pick next. Can't we use some of that
Yeah, you can.
logic here to identify potential backdoor variables?
Potential backdoor variables would be harder to identify, but those notions get used in the randomization strategy. So which variable to pick in the next random restart, we use a lot of heuristics, which is a slide I skipped, but I put it online. You're welcome to read it, it's self-explanatory. So if you have searched this part of the state space, you will try to randomize in a way that you search another part of the state space. So that's typically the randomization heuristic. But identifying automatically what is the backdoor is a known NP hard problem again. So I don't know how much we can do there, but I don't know complete part of the literature, so I should